In this video, I want to go through the Nastran coordinate systems, orientation vectors, offsets, and deflections. There is a lot of information that you can possibly miss when it comes to coordinate systems in Nastran, so I want to take a few minutes to go through some useful pieces of information that might help you out. Now, the first thing I want to do is go over this concept of the observer. I think if you understand this concept of the observer, understanding the coordinate systems might be a little bit easier. And then I want to point out where I'm getting a lot of this information. We'll do a quick overview of the various different types of coordinate systems available in Nastran. I'll have some comments on the reference and the displacement coordinate systems for grid entries. And then this is where we are going to have a discussion on vectors and displacement coordinate systems. So we're going to be talking about deflections, orientation vectors, offsets. After that, I'll talk about units in some of these coordinate systems, and then some final comments on element coordinate systems. So to start off with the observer, whenever you're working with Nastran, you always have to think of this concept I like to call the observer. Whenever you're looking at a deflection, whenever you're creating a vector, whenever you're looking at a stress result, you have to ask yourself, from what observer's perspective are you viewing that information? So you might have this coordinate system like this. You might have some other coordinate system that might look something like this. And then here, maybe I'll flip one. So this is X, this is Y, and then maybe this is Z. What I like to do is, whenever I look at a coordinate system, I always like to think that there is an observer on that coordinate system. So here I'm representing the observer with a bunch of stick figures. And looking at coordinate systems from this perspective of the observer has helped me a lot when it comes to understanding vectors, displacements, stress results. So this is the first concept I would like you to carry with you after this video. Now, after this, where am I getting a lot of this information from? So if you refer to the Nastran reference guide, there's a chapter called Grid Point and Coordinate System Definition. If you look through these paragraphs, most of the information I'll be covering today is in this paragraph. And it's unfortunate that it's only these two paragraphs where you discuss the concepts that I'll be covering. If you happen to miss this section, if you skipped over these few sentences, you are going to miss some very valuable information. So here I'm just pointing this out. So if you want to learn, or if you want to read where I'm getting this information, it's coming from these two paragraphs in the Nastran reference guide. And again, this is in chapter or section Grid Point and Coordinate System Definition, which happens to be in chapter 2, Grid Points and Coordinate Systems. Okay, let's talk about the various different coordinate systems available in Nastran. So here, let's talk about the rectangular, the cylindrical, and the spherical coordinate system. Now, I'm not going to discuss how to set these up. I'm going to discuss how to interpret these coordinate systems. Now, let's suppose here at the bottom we have one coordinate system, X, Y, and then Z. And then here we have another coordinate system, cylindrical. So this is going to be the R, the theta, and then you have the Z. And then here for spherical, you might have something like this, R, theta, and then phi. And then here, let me draw 2 points. So here we have 1 point. In the cylindrical coordinate system, we might have 2 points, and then for spherical also we might have 2 points. Now, when you define the position of these points for rectangular coordinate systems, you might use a XYZ coordinate. And then for cylindrical, you might use a radius, a theta, and then a z. And then for spherical, you might be using a radius, a theta, and a phi. Now, be very careful when it comes to the spherical coordinate system, because depending on who you speak to, they will have a different definition or a different order for these components. So if we look in the quick reference guide here, we see that the order is a radius, a theta, and a phi. So we'll go ahead and write radius, theta, and phi. When you look online and look for more information on the spherical coordinate system, be very careful, because as you see in this table, different communities will describe this coordinate system a little differently. Sometimes they switch the theta and the phi. Sometimes instead of r, they use the letter rho. So just keep that in account whenever you're doing research online. Different communities will use different characters and might use a different sequence of the components. So this is how you define the position. Now, when you specify position, there are these so-called unit vectors that you get at that position. So what do I mean by this? For the rectangular coordinate system, the unit vectors are parallel to the original coordinate system, if you will. So here we have a unit vector x hat, a unit vector y hat, and then a unit vector z hat. And the same for this point, x hat and a y hat, and then z hat. Now, for the rectangular coordinate system, these unit vectors are parallel to the original coordinate system. Now, for cylindrical coordinates, the unit vectors are a little different. So what you do here is you draw r first, and then you rotate it. After you rotate, the tangent is going to be the so-called theta hat. And then from the origin to the point, you can draw a line, and this would be your r hat. And then here, the z hat would just be parallel to the z-axis. So it would look something like this. So these are the unit vectors, and you can think that for each of these axes, you get a x hat, y hat, and a z hat. So then at this point, you get this local coordinate system that's defined with these rectangular coordinates and this x hat, y hat, and z hat. Now, let's repeat this for this other point. So we're going to swing theta here. So then the tangent looks like this. This is our other theta hat. Our r is going to go from the origin to that point. So this is what r hat looks like. And then z is just going to be parallel. So this is our z hat. And here, this is our x hat, our y hat, and then our z hat. So you can see that in the cylindrical coordinate system, depending on where the point is, the unit vectors are going to be oriented differently. And the same can be said for the spherical coordinate system. So here, let's go ahead and try and draw some unit vectors. So the first component is actually going to be phi. I know the spherical coordinate system does get a little complicated. So here, you're actually rotating by phi. So this would be your phi unit vector. And then here, this would be your theta unit, or sorry, your r unit vector. And then theta, that actually swings like this. So this would be your theta unit vector, and I understand it honestly gets a little complicated, to be honest. So then here, now for the spherical coordinate system, r hat, v hat, and theta hat, you might be asking, okay, which one's the x hat, which one's the y hat, and which one's the z hat? If you refer to the Nastran reference guide, after those 2 paragraphs I mentioned, you get these figures 2, 2. If you refer to figure 2.2c, this tells you what the, what the unit vectors are. So here, if you look at the r direction, this would be your first component. So this would be the x. Let me go ahead and put this side by side. So this r component would be x hat. And then the second component would be the theta hat. So here, let's go ahead and write y hat here. And then for phi, that would be z hat. So let me quickly summarize this page. Number 1, depending on where you are in the coordinate system, and right now I'm saying this for cylindrical and spherical coordinates, depending on where you are in that coordinate system, your unit vectors are going to point in different directions, and this is going to be very important later on. If we're working in a rectangular coordinate system, fortunately life is a little easier here. Your unit vectors are parallel to the original coordinate system that you see here. So here x hat is parallel to the original x-axis. Okay then, so after this, let's go ahead and talk about the grid reference coordinate system. So here we're talking about grids and the reference coordinate system. And so like before, we're going to talk about rectangular, cylindrical, and spherical coordinate systems. So here at the bottom left, we're going to define a coordinate system. So I'll say it's x, y, and then z. And then here, we're going to draw a point. Now, let me manually type up a grid entry. So we'll call it grid. We'll call it grid 1. Maybe we'll assign this coordinate system a CID of maybe 101. So here we're going to reference the coordinate system, and then we're going to say that the point is located at 1, 1, 0. So 1, 1, 0. Now here, what we're doing is these few fields. So this would be the CP field, the X, the Y, and the Z fields. This would be the first field, and this would be the grid ID. So these first few fields, I like to say that this is being viewed from the constructor observer. So what is the constructor observer? Here at the coordinate system, here at the bottom left, I like to draw a stick figure here, and then I like to put a hat on him. This is his construction helmet, if you will. It's in this construction observer, it's in this perspective where we put the point in space. And let's do this for a different coordinate system. We'll do this for the cylindrical coordinate system. So we have a point here. We have our construction observer here. It's in this perspective where we place the point. So here we'll say that the point is maybe located at 1, 45 degrees, and 0. So this point is in this construction observer perspective. So what does the grid entry for this look like? This might be grid 1. This coordinate system, I have an ID of 2 maybe. So we'll put 2 there. And then here for x, we'll put a 1. For y, or the second component, we'll put 45 degrees. For the third component, we'll put 0. And let's go ahead and do this for the last coordinate system, spherical. So we have r, theta, and phi. And then we have a point there. We're going to say that the point is 1, 45 degrees, and 0. And this is all from a different observer, which is the construction observer's perspective. So this is what a reference coordinate system is on a grid entry. It's the constructor's observation coordinate system, if you will. Now, after these first few fields, and here, let me draw the grid entries. So grid 1, and here we'll say that this coordinate system has an ID of 3. So here we'll say 3, and then we'll put the coordinates 1, 45, and 0. Now, these fields, the CP field, the X, the Y, and the Z, the CP field, the X, the Y, and the Z, these fields are used to position the grid in space. But then we have another coordinate system that is called the displacement coordinate system. So displacement coordinate system. So in this coordinate system, this is where you're going to be observing the displacements. You're going to be observing any vectors, any offsets that you define. So let's go ahead and talk about the displacement coordinate system. So what does that look like? So let's do this for rectangular, cylindrical, and spherical coordinates. Okay, for the rectangular coordinate system, or this is the way you can understand the displacement coordinate system for the grid entries. So say you've defined this coordinate system here at the bottom. Let's give it a CID of 1. Let's do this for cylindrical 2, and R at theta. And a Z, this is a CID 2. And then we'll do this for spherical coordinates. So we'll draw a coordinate system here. And we'll give this a CID of 3. So what is a displacement coordinate system? Let's go ahead and draw a point here, 2 points here and here, and then 2 points for the spherical coordinate system. If you recall, each point has its own set of unit vectors, if you will. So that's what I'm drawing right now. So here we're drawing unit vectors for the rectangular points. And we'll go ahead and do that same for the cylindrical coordinate systems. So here r hat, which is x hat, and then theta hat, which is y hat, and then z hat would be in this direction. So this would be a z hat, and then z hat. And then same for this point. We draw r, x hat, theta hat, and then we draw a z hat. And while I'm finishing this last one, again, the unit vectors depend on what coordinate system you're in. It depends on where you're at, or it depends on the point in space. So here, let's go ahead and draw some unit vectors here and here. And this is going to be our phi, which I believe is the y hat. Nope, I got it mixed up. And then here we'll go ahead and draw phi here. And then we have a theta hat. And then again, this is all described in the Nastran reference guide, chapter 2. So let's go ahead and finish this. Okay, now when you define the displacement coordinate system, you're talking about these individual unit vectors. So let's go ahead and do this. Each of these unit vectors, and I'm going to be removing some of the labels here just to clean up the screen. Every grid is going to have its own inherited observer, if you think of it. So here, we always like to think that there's an observer at the coordinate system. But what happens when you define a displacement coordinate system, you're actually defining multiple observers. So here, let's go ahead and draw all these different observers. And then you can see that it gets very complicated very quickly. And then here, let's go ahead and draw some observers here also. So each observer's orientation is going to be different. It's in these observers' perspectives where you're going to be observing the displacements and where you're going to be creating your vectors. So you can think of orientation vectors. You can think of offsets. So let me repeat this again. It's in these displacement coordinate systems where you're going to be observing the displacements of the nodes, any vectors that you've defined at the grids or the nodes. You're going to be observing this data in those different observers' perspectives. So even though you define only one displacement coordinate system, what's actually happening, each grid is given its own displacement coordinate system. So then let's go ahead and draw some grid entries. I think let me go ahead and go here. So I'm only going to draw or write out 3 grid entries. So there's going to be a grid entry for this point, maybe 1, a grid entry for this point, maybe 2, and then a grid entry for point 3. So then let's go ahead and do that right now. So grid, maybe 1, and the CID is 1. And then here we're going to put the point, maybe it's at x equals 1, y equals 1, and 0. Grid 2, and maybe that's going to be at 2 in coordinate system 2. So this is the construction coordinate system right now. 1, 45 degrees, and then 0. And we'll go ahead and repeat that for the third point. Grid 3 in coordinate system 3 is going to have these coordinates and 0. So let me go back here, see if I have points assigned. 145, okay. And then here I need to define the coordinate system, so there would be a coord 2r maybe. It has the ID. Let me do this. This is getting a little confusing, so maybe what I'll do is I'll give these points a different ID. Go ahead and delete that, and let's relabel some of the values back here. So at the bottom left, this is coordinate system 101, coordinate system 102, and let me make sure I'm doing this accurately. Oh no, this is still coordinate system 1, coordinate system 2. This is point 101, point 102, and then point 103. And so that's where we're at here. And then I need to create all these different coordinate system entries. One for the rectangular, one for cylindrical, and one for spherical. And all of these have different IDs. So here we've only defined the fields that are used by the construction observer. So that would be field 2, 3, 4, and 5. And then here, let me make sure. Let me make sure I have the grids properly defined. Let's just go ahead and look at the quick reference guide and navigate to the grid entry. So here, if we look at this, right, everything looks good. 1, 2, 3, 4, 5, 6. Right, perfect. Okay then. So let's go ahead and define the displacement coordinate system for each of these grids. If you go to this field, which is field 1, 2, 3, 4, 5, 6, and 7. In field 7, this is where you specify the displacement coordinate system ID. So here for the first point, we're going to say use coordinate system 1, use coordinate system 2, and then use coordinate system 3. But remember, we're not defining one displacement coordinate system. Each grid is going to have its own displacement coordinate system that depends on the position of the point in that coordinate system. If you're talking about rectangular coordinate systems, usually the displacement coordinate systems are parallel to the original coordinate system. Whereas in cylindrical, the unit vectors are going to determine the displacement coordinate system for each grid. And then if you see here, I'm going to delete this. You're going to have a displacement coordinate system again for every point. So here I'm using a stick figure to represent all these different observers that you're creating. And again, it's in these observers perspective where you're going to be observing the displacements, vectors like orientation vectors and offsets. Okay then, let's go ahead and go on to the next section. This is where we get to talk about vectors. So let's go ahead and jump to the next page. Or maybe let's duplicate this. Let's go ahead and delete some of this data. So when you are referring to a vector at a point, this is how you can look at the vectors. And I think it might be better if I just repeat this. Let's go ahead and do this again. So vectors. So we have an x, y here. So this is going to be rectangular, cylindrical, and spherical. Let's go ahead and draw this now. So this is our r, theta, and phi, r, theta, and z. So here, remember, there is a x hat, a y hat, and a z hat for every point. So vectors are observed in the displacement coordinate system. So that's one key thing you should know about vectors. And here there's another vector here. So this would be its x hat, it's a y hat, and then z will be coming out of plane. So this is a z hat, and here we'll draw a vector, a unit vectors for this point. So here we have x hat. This would be I believe phi hat. So this would be I believe the y. Let's go back and see. Right, z. So it's z. So let's go ahead and draw z. And let me just double check in the reference guide just to be 100% sure. I'm looking for what the value is here. So this would be, right, phi. So this would be my z hat. And then y would be in this direction. So again, the vectors are observed in the displacement coordinate system. So remember, there is an observer here at this point. There's another observer at this point. And then here, there is an observer here. So say we want to define this vector. If you look at the top right, I want to define a vector that looks like this. This vector is actually different for each observer, for each displacement coordinate system. So here, for this first observer, for this first displacement coordinate system, this vector from the top right might look something like this. So we start here at the bottom left, we walk along the x, we walk along the y. So this is what this first vector looks like for this displacement or observer. For this point, for this observer, we walk along the x and then we walk along the y. And this would be the vector for this observer in this displacement coordinate system. And then we'll repeat the same for this one. So we walk along the x and then we walk along the y. And so the vector will look something like that. And say we have another point. So here we'll look at the cylindrical coordinate system. Let's go ahead and draw another point. So this is going to be x, y hat, and then z hat would be out of plane. Let's draw the vector from the top right here. We walk along the x1, walk along the y1. So here, this is what our vector will look like for this observer. So this is the vector. So you can see that depending on where the point is in space, that vector might be oriented a little differently. So keep that in mind when you're working with vectors. So now let's go ahead and talk about orientation vectors. And let me make sure we're following the agenda here. Actually, let's go ahead and have a conversation about displacements real quick. Duplicate. Let's talk about deflections. When you look at deflections from Nastran, the deflections are vectors observed in the displacement coordinate system. So suppose you had the deflection at the top right for each grid. So then it's the same procedure as before. Depending on what the displacement coordinate system is, use that observer, use that displacement coordinate system to look at your deflections. So here, if we were working with this deflection here at the top right, like the discussion before, you first go to that observer. So here at the rectangular coordinate system, we go to the observer, and it's in this perspective we view the deflection, we view that vector. In the cylindrical coordinate system, it's the same thing. For this point, this is our observer, this is our displacement coordinate system, and this is the displacement that this observer views. For this other point here, this observer is oriented like this, and this is the deflection this observer views. And here for spherical, it's the same thing. You have an observer, you have an observer in the displacement coordinate system, and it's viewing the deflection in this manner. So remember, you have an observer, and you have this observer oriented in those unit vector displacement coordinate systems, if you will. So this is very important that you think about this. So let's go ahead and continue on. That was deflections, and now we can talk about orientation vectors. So with orientation vectors, everything that I've said for vectors, everything I've said for deflections is the same thing. You have an observer in the displacement coordinate system, and the vectors you define are in that observer's perspective. So keep that in mind. For any vector at a point or a node or a grid, it's always this, a displacement coordinate system, and it's in that coordinate system where you define your vectors. Now let's talk about orientation vectors. So typically you use an orientation vector when you're working with the C-beam element, when you're working with C-bar, or when you're working with C-bush. Typically what happens is you first have a point GA, and then you have a point GB, where both of these points are maybe grids or nodes. After you have GA and GB, by default, it's assumed that this axis is the X element axis. And then you have this orientation vector that's defined in GA's, how do I say, displacement coordinate system. Remember that. So here's GA, and then here's our observer. So it's in this coordinate system, this observer's coordinate system, where you define the vector. So here, let's assume this is our coordinate system, and then maybe our orientation might be something like this. So we go along the z, and then we go along the y. So this vector might look something like this. So this would be 0, 1, and then negative 1 maybe. So this vector again would be negative, or 0, positive 1, and then negative 1. And remember, this is in the displacement coordinate system, the observer's coordinate system. Now, once you have this orientation vector, how do you get the y element axis for the C beam? How do you get the y element axis for the C bar or the C bush? So here, you would do some cross products. So here, let me draw Z element, which is unknown at this point, and then we draw the y element axis, which is also unknown at this point. So one common question is, okay, so I know my x element axis, I know my orientation vector, how do I get my z element and my y element axes? Here at the bottom right, you would need to use the cross product. So the z element axis is equal to the cross product between x element and the orientation vector. And then the y element axis is the cross product between the z element axis and the x element axis. And now the question you might have at this point, in what coordinate system are you observing these values in? So it's really up to you what the coordinate system is. Here, if we're thinking about this, let's see, it can actually get a little complicated. So I'll let you to carefully ponder in what coordinate system we're viewing these different vectors. Here, I'm going to be assuming that the reference coordinate system, we're going to assume that's the basic coordinate system, CID 0, and the displacement coordinate system is also the basic coordinate system, just to keep things simple. I think once you're in the spherical or displacement coordinate systems, things get a little complicated. So let me quickly summarize this. Number one, your orientation vector is defined in the displacement coordinate system CS of GA. And then you do the cross product to get the different axes for that element coordinate system. So this is how you would use the orientation vector. Now let's talk about offsets. And one thing to keep in mind here is that, again, if we go back to that discussion on vectors, any discussion on orientation vectors, the same concepts about vectors applies to orientation vectors. And here on this page, we're going to go over offsets. An offset is also a vector. So anything I spoke about regarding vectors also applies to offset vectors. So offset vectors, you would use these also if you're dealing with a C-beam, a C-bar, or a C-bush, and a few other elements. So what is the offset vector? Suppose you're dealing with the beam, and this is our GA, and this is our GB. Typically, the shear center is along GA and GB for a C-beam element. So let's go ahead and write C-beam here. So this dotted line is the shear center. Suppose you want to offset the shear center. How would you do that? So this would be our new shear center point. And then this is maybe the cross section for the beam. So here, this offset, I'll call it O1. It's a vector. This is in the displacement coordinate system of GA. And then here, this offset is in the displacement coordinate system of, and I'll call this a vector O2. This is in the displacement coordinate system of GB. So again, these vectors are defined in the displacement coordinate systems. So I wanted to point that out. Now let's go over the units. So here, let's go ahead and talk about units. So far we've spoken about the so-called reference coordinate system for grids. And we've talked about the displacement coordinate system. So here, we gave this another name. We called it the observer, the construction observer. So remember, this is, if you really want to think about it, this is a stick figure with the construction helmet. It might look something like that. This displacement coordinate system, I call this just the observer. And then here, I also give it a stick figure of its own. Sometimes you see this referred to as the analysis coordinate system, which further confuses us, but here, let's go ahead and just call it the displacement and the observer. So let's go ahead and talk about the units. If we have a rectangular coordinate system, a cylindrical, and then a spherical coordinate system, what are the units? So here we have an X, Y, and Z component. For cylindrical, we might have a radius, a theta, and a Z. And then for spherical, we might have a radius, a theta, and a phi. So here, L for length, L for length, L for length. So this could be X, Y, and Z have units of length. So think about meters, inches, so on and so on. Here, radius is a unit of length. Theta is a unit of degrees. So I'll use the degree symbol here. And then Z has a unit of length. For spherical, R will have a unit of length. Theta and phi are both units of degrees. So let's go ahead and write some parentheses here. Now, this is for positioning. Remember that. We have a construction observer that we use to position these points in space. We've looked at what the different units are. Most of these units are in length, but some of these units are specified in degrees. Now for the observer, what are the units for the observer? So like before, we're going to have a rectangular, a cylindrical, and spherical observer. So we saw that when we look at the translations, at least, the translations are not, or rather the translations are viewed in different observers' perspectives. They're all viewed in their own individual X hat, Y hat, Z hat coordinate systems or observer coordinate system. Remember, think of X hat, Y hat plus Z hat. So this is what the observer is looking at. So when you look at, say, translations, writing on a tablet is very difficult sometimes. Okay, well, that's just translations. This is going to have a unit of length, and the same is true for the other one, length. So you could have meters, kilometers, inches, or feet. or miles depending on the unit of length that you're using. Now, what about rotations? What would that look like? So you're going to have a rotation about the x hat. And what do I mean by this? If we look here at the F06 file, we have this table called displacement vector. So I think it might be worth showing another image. So we have the rectangular, the cylindrical, and the spherical coordinate systems. So here we'll quickly draw the different coordinate systems. And here we'll go ahead and draw some points. Each of these observers, we'll go ahead and quickly draw our observers. And then I think this observer was almost upside down. All of these observers are going to report the displacements to the F06 file. So this observer is going to report displacements. This observer is going to report displacements. This observer is going to also report its own displacements. And you can see that depending on where you're at in space, each observer is going to be reporting its own displacement. So here, this observer for this point is going to report its own displacements. So this is all contained in this table, displacement vector. So you have the X, Y, and Z components, and then here you have the rotations about those X, Y, and Z axes. So if we go back to the units page, you have a rotation about Y hat, a rotation about Z hat, and then the same is true for the other ones. Now, the question is, what units are these rotations given? So the units are radians for all of these rotations. So here, radian, radians, and what I want to make it clear is that all of these rotations have units of radians. Now this is a big difference because when you define the position, you're using units of degrees, but then when you look at the observer's output, you see that you're using radians again and again. Okay then, so that is the comment on units, and now let's talk about element coordinate systems. Element coordinate systems. So at the very beginning, I came up with this concept of the observer. So we've been using stick figures to represent this observer. This observer has its own X hat, Y hat, and Z hat, if you will. If we look at a beam, here let's go ahead and draw a beam. So its coordinate system might look something like this: X element, Z element, and a Y element. And then here's our observer. So we might have some shear forces, we might have some moments, we might have a torque. So when you look at the beam results, these results are being reported from the observer's perspective. So if there was another beam, and let's go ahead and see if I can draw another. So say we have this beam here. So this would be maybe the X element, and then this would be maybe the Y element, and then this would be the Z element, and then here in the middle would be the observer. So it's in the observer's perspective where we observe our internal loads or our stresses, shear, moment, torque, or so on and so on. So what about 2D elements? What does that look like? So every 2D element, has its own coordinate system: X, Y, X hat, I'll call it Y hat, X hat, Y hat, x hat, y hat. So let's go ahead and draw some observers. So there's an observer here, an observer here, an observer here. So for each observer, there's going to be a sigma. If we're dealing with stress, there's a sigma x, a sigma y, and then there's a shear stress. So here, suppose we have the F06 file. All of these observers are going to report their own observed values for sigma x, sigma y, and the shear stresses, and so on and so on. Now, this becomes a problem in the following situation. So we're still talking about 2D elements. What happens if you have this very simple scenario? Let me go ahead and look in Patran. Okay, let's go ahead and do this. Suppose you have two triangular elements with the force here and here. And let's go ahead and look at the coordinate systems for this. So we'll go ahead and plot those. So this is our x element and y element. And then our x and y here would be different. So this is our x and y element. So you can see that the element coordinate systems for these two elements are different. And here, again, we're applying a force here and here. Here the observer might look something like this. This observer might look something like this. So now, let's look at sigma x for this element. So sigma x for element 1, I think it's called. Let's go ahead and see what the element is. All right, so this would be element 1. And then sigma x for element 2. And then we'll go ahead and look at the sigma y for element 2. So when we look at the results, we're tempted to say, okay, we see a sigma x. This must be in maybe the global coordinate system, if you want to call it that today. It's technically not called that. It's actually technically called the basic coordinate system. When you look at the stress results, you look at a sigma x as an example, you might be tempted to say they're all being viewed from this coordinate system, but that is not the case. They're being viewed from these individual element coordinate systems. And here, just to prove it, let's go ahead and see what the results are from this very simple analysis. So we'll go ahead and look at the results. So for the x, we're getting about 20 for element 1. So let's go ahead and draw that. We're getting about 20. And then for sigma y, we're getting about 0.56. So let's go ahead and draw that. And here I'm looking here. So this is sigma x and sigma y for the first one. So we're getting about 20 for x and then about 5.8. So 5.8. And then for the second element, what are the values? So this would be the second element. We're getting about 0.6 and 20. So let's go ahead and write that. 0.6 and 20. So you can see that. Let me draw this here. For the first element, the stress for the first element is sigma x equals 20. For the second element, if we look at the stress that's being reported in the y direction for the second element, it's actually 20. So here what I wanted to demonstrate, whenever you look at a displacement, whenever you think about a vector, And I think this would be a great way to end. Whenever you think about a vector, a deflection, which is a vector, whenever you think about an orientation vector, whenever you think about an offset, whenever you think about a beam result, whenever you think about a 2D element result, like maybe stress or element force, you always have to think, in what observer's perspective are you viewing the results? And as you've seen in this short, or I guess at this point it's a little longer in this video, the observer's perspective, the element coordinate system, the displacement coordinate system, this can honestly vary. So whenever you're looking at data from Nastran, always ask yourself this question: in what observer's perspective, in what coordinate system am I viewing the results? So then I think that brings us to the very end of this video. Like I said, what I wanted to do in this video was to introduce this concept of the observer. We've seen throughout this video that this observer could have different orientations depending on if it's a grid or an element. It's in this perspective where you're getting data, say in the F06 file, you might have displacements, you might have stresses as an example. If you're working with the bulk data file, you might be defining offsets, you might be defining orientation vectors. All of this data is being observed from different observers. So it's very important that you understand that. Here, let me go ahead and draw this. It's very important that when you think about the Nastran coordinate systems, so there's an X, a Y, an X, and a Y. When you're defining these coordinate systems, what you're actually doing, you're defining all these different observing coordinate systems, if you will. So that's how I would think about it. So with that, I'll go ahead and stop there, and thank you so much for watching.